very much for the opportunity to give this series of lectures and for letting me stay in Chicago for 2 weeks. This has been a really nice trip so far. Everything I want to speak about is joint work in progress with Lucas Mann. Being written now. But for the first maybe 2/3 of this talk, I just want to do sort of review of things that are already in the literature, mostly stuff that's in Fargues-Scholze, and sort of how one might think about some of the constructions there. And let me start with some really big picture discussion just for a few seconds. So back in 2014, Fargue had this kind of amazing idea that if you stare at things correctly, local Langlands for non-Archimedean fields should in some sense just be geometric Langlands over the Fargue-Fontaine curve. Okay, this is sort of a really remarkable idea, and it takes a lot of technical effort to make this into precise mathematics. And sort of between 2014 and 2021, Fargues-Scholze sort of refined this from a vision into sort of a precise set of constructions and tools. So now we sort of have enough machinery to talk about the structures that you would want to make sense of this. And they wrote this incredible paper laying this machinery out, and they already used this to do some very remarkable things. So constructing a semi-simple local Langlands correspondence for any group, for instance. And at the very end of this paper, they state some kind of categorical upgrade of the local Langlands conjecture, which is modeled on the geometric Langlands conjecture in its sort of original form for complex curves or curves over algebraically closed fields. And so the point of this series of talks is to kind of try to take a step past Fargues-Scholze and see can we actually make some progress on proving this categorical form of local Langlands. Okay. So having said that, let me begin with some sort of known stuff. I want to pick up where some of Sasha Pinkman's talk this morning left off. So let's start with some recollections. Bung G. So this will mean something very specific in our setting. So throughout all of this, I will fix some G. I will take for simplicity my base field to be QE, not some random finite extension. And also for simplicity, I will fix G to be split, just to make the notation more streamlined. I don't have to worry about L groups versus dual groups, etc. Yes?
Is G reducted?
Yes, split reducted. Oh, sorry. Split connected reducted. And I'll also fix the Borel and maximum torus in G. So Bung G, let me start by sort of defining this, and then we'll unwind how to think about this, sort of for at least half of the talk. So Bung G, so this is the stack, this is the functor from perfectoid, let's say affinoid, perfectoid spaces over FP bar. So this is just the sort of opposite of the category of rings we were looking at in Sasha's talk this morning, towards groupoids. And what does it do? It takes some test object S towards the groupoid of G torsors. On this relative Fargue-Fontaine curve over S. Okay? And you may wonder right away what exactly do I mean by G torsor, because there's several ways to make this precise, and maybe the simplest way to do this is to think of these as tensor functors from the representations of G towards vector levels on this. Okay, that's maybe the simplest way to set this up. Okay, so that's a nice definition that you can make, but where to start in terms of unwinding this thing. So let's start by discussing the topology. Of this thing. And let me even start with the case for G is GLN, because this will connect very closely with what we saw this morning. It'll just amount to recasting some of it in slightly different notation. This is as a warm-up for the general case. So recall from the talk that we saw this morning stack like this, talk about its set of points. This means kind of what you think it means. It means you take the points over algebraically closed fields. These form some groupoid, sort of kill all non-trivial isomorphisms. It's just a set of isomorphism classes. And we saw this morning that this set is very explicit. This is just a set of rank n Frobenius isocrystals over R. This is by this map that Sasha denoted m goes to E of m, right?
So Frobenius is a crystal is the same as F as a crystal.
Yes, yes, sorry, F. I can even write that if you prefer. It's shorter for me. Okay. And these, if I do the Mann classification, these are also just totally of combinatorial nature. You can take an isocrystal and you can characterize it by sort of slopes. We already saw these this morning. If you put these sort of in a list where you count them with the right multiplicities, vector slopes of the Newton polygon. Of m. So this actually just loses no information, and you can characterize exactly which sort of slope vectors you're getting. Just announce the requirement that Newton polygons have integer coordinates at different points. Right? So this, as a set, is an extremely combinatorial, simple thing.
Just so it's a subset. What is lambda here?
So then these are the slopes from Sasha's talk, these rational numbers, and you count them with the correct multiplicities. And so this, this will be an element of e to the n, let's say, plus, where plus means sort of weakly decreasing sequences. Right? So you take the biggest slope, you count it with the appropriate number of times, then the next biggest slope, appropriate number of times, etc. Okay? And of course, the requirement is just that the denominator of this slope times the total width of that section of the polygon has to be an integer. That's the only requirement. Okay? Reasonable? So the first thing I want to talk about is what this sort of becomes if you replace GLM with general G. And the answer is very nice. So for general G, will it be of G? Be the set. Well, most simply it can be described as elements in the G points of the completed maximal and ramified extension of QP, and then you put a funny equivalence relation on this, and when you declare that G is equivalent to sigma H inverse. This is the set of sigma conjugacy classes in the QP unramified completed points of G.
And sigma is your notation for kind of
sigma is the canonical lift of the P power Frobenius. That's right. That's right. And so this has a much better, more conceptual interpretation, not in terms of equations. So this is the set of F isocrystals of G structure over FP. Okay, so this was introduced by Koppitz. This is often just called the Koppitz set. And yeah, in the case of GLN, you just get back this story, of course. They're an element of this set is nothing other than a rank n isocrystal. But in general, it's a little bit more subtle to describe a general element of this set by combinatorial means. So let me briefly recall this aspect of Koppitz's theory. So we have two maps. I should really attribute this. Two sort of canonical maps out of this. One of them is a natural generalization of this sort of operation of taking the slopes of the Newton polygons. This will go from this set towards dominant Q rational co-weights into T. It's usually called the Newton point. You should think of this as like the slopes of the Newton polygon. And there's another map which is a little harder to describe, and I actually won't define it, but its target. Most people, maybe a lot of people say initially its target is this algebraic pi1 defined by Borovoy, but again by some basic result of Koppitz. You can also canonically think of this as the character group at the center of the Langlands school group of G. And that actually will be important for us later. And so this is pronounced B goes to kappa B. And this is usually called the Koppitz map. Okay. Neither of these maps gives you complete information about this set, but together they do. So the map from this into the product of these two sets by this pair of maps is injected. Koppitz characterizes its image completely, in fact, for all quasi-split groups. And there's even more structure here, and all of this will be relevant when we come to the Bung story. Moment. So in here, there's a distinguished subset of elements that are usually called basic. So these generalize the isocrystals in the GLM case that have a single slope with whatever multiplicity and no other slopes. And one way to define these is as the elements whose Newton co-character is in the kernel of the map from here to rational co-characters into the adjoint group. So this B such that, let's say, this equals 0. Co-characters into G adjoint. Rationalized. I apologize about that a little bit. Right? Okay. Sort of all the slopes are the same, so you should think of this. And there's a very nice miracle, which is that the composite map from this into this, and then composed with the Koppitz map, is actually a bijection. So another way to think of this is that this Koppitz map kappa has a canonical section. Okay, so now let's come back to Bung. So let's think for a moment about what Sasha did this morning. He wrote down this recipe that goes from an M to a bundle that he was calling E sub M. If you stare at this recipe, you realize that it is a tensor functor, first of all. It's compatible with tensoring isocrystals versus tensoring bundles. And moreover, this Koppitz set, as I've defined it, well, it's the set of F isocrystals with G structures, so you can think of it in a Tanakian way, right? If I have an element G in here, for every representation of capital G, I can push it out along there and I will get an F isocrystal with G structure.
In the case of GLM,
yeah.
What is this section?
It is the degree. It's the vertical coordinate of the rightmost endpoint of the Newton polygon.
So
yeah.
In the case of GLM,
yeah.
So this map to by B sub B probably.
Yeah.
What does it do? So you have this isocrystal lambda
yeah.
1. So it remembers only lambda I. What does
it remembers lambda. It remembers the slopes of their total multiplicities. Right. If you draw the polygon, it remembers the slope lambda I with multiplicity, the total width of that part of the polygon. Right?
Sorry, but what does it
So for an elliptic curve, semi-stable elliptic curve, you would either get 1, 0, or a half comma a half.
Yeah, but you're saying that this map forgets something. What does it forget?
No. For GLN,
for
GLN, this first map is enough, in fact. And in fact, any group which is split with simply connected derived group, the first map is enough. But for, let's say, SO9, the first map is not enough. Yeah. GLN is a little misleading. You don't need the second map for GLN. For GLN, the second map just remembers the 3. Other questions? Okay. Now let's go back to this Bung story. So for any G, you get a map, and in fact, if you're careful, you see it's even a map of groupoids from B of G towards isomorphism classes of sequence of this stack for any algebraically close this one C. And I denote this by B goes to E, B, and later it'll be important for me to maybe notate the field. Okay. So this is some totally canonical thing that you can do, and it's just again by interpreting this in the Tanakian way and post-composing with the recipe that Sasha wrote down this morning. So for any B, again, I get a tensor functor from representations of G towards vector bundles on the curve, and it's exactly how I'm defining Bung. Okay. So for general groups, it's a bit harder to see that this has the following property. So this is a group Fargue. This induces bijection. Topological space of this stack. Let's call it set B of G. Okay. This is real for all G. There's also a version of this for general, possibly equal characteristic B local fields, and there it's actually a little bit harder. Result is functions. But I will stick with mixed characteristic for these talks. You can say even more. So this Bung, I didn't quite tell you the sort of topology of it, but it's a priori it's some sort of just pre-sheaf of groupoids on this category, but it's actually a stack for some very fine topology. And although it's a little frightening at first, you can define a topological space for it. And so this set, which a priori is just a set, comes with an intrinsic topology. And you can even characterize this intrinsic topology completely. So this has an intrinsic topology, right, which a priori is somehow not related to the structure of this set, just is what it is. But it turns out to be completely explicable. So here, state this in two parts. So the first part is Fargues-Scholze. This is the map. So I take this, I identify it with B of G as I did above, and then I have this funny Coppit's map out of here. And from now on, I'll think of the target of this map in terms of the second option I wrote down for it. So this map induces bijection. From the set of connected components of this stack onto its target. And you can say a little bit more. I'll come back to this when I draw some elaborate picture in a minute. So this tells you that the connected components of this stack are indexed by the target elements of this target with this Coppit's map. I also told you this Coppit's map actually induces a bijection when you restrict it to some canonical subset of B of G. And the point in Bung given by that section plays a distinguished role. And so each connected component Bung contains a unique point, and I'll put three different adjectives here to pick your own favorite. Well, I'll start with the word that is given, contains a unique basic point, but you can also think of this as being semi-stable in the usual sense of Harder-Marsimon production theory. And I told you to have a topological space, and it turns out that this point as a singleton in that space is open. Okay, so all three of these interpretations are useful. Oh, sorry, this was part one.
And it's also dense. It's also dense.
It is also dense. Each component of Bung contains a unique point which is open and dense, and the closure of that point is the whole component. All the other strata are negative dimensional. I'll come to that in a second. So this is part two. And so part two says you can actually completely describe the topology on Bung. And so this was first proved by myself for GLN and then by Fima theorem is that the map referenced by projection between this topological space and this set, this is a homeomorphism. For sort of the obvious partial order topology on here, so I'll call this for the Newton point. Polygon. Okay. And so the point is that on the target of this Newton map, there's a natural partial order given by the usual sort of dominance order, right? Say nu1 is above nu2 if the difference is a non-negative combination of positive roots. And in human terms, this just corresponds to polygons that sit above or on another polygon with the same endpoints, right? And I want to emphasize something that I'll come back to in an example later, which is that for people who like to think about isocrystals over schemes and positive characteristic, we're used to this phenomenon that, say, a family of elliptic curves will be sort of generically ordinary, and then it'll jump and be super singular in some closed subscheme. Here the opposite happens. This is much more like reduction theory of bundles over proper curves or something. Sort of generically, your polygon is as straight as possible, and then on closed subsets, it jumps and becomes more angular. Okay?
So from the point of view of formal groups and so on, it's counterintuitive.
It is counterintuitive. Yeah, this switching of topologies.
But this is live, and maybe you will eventually explain why this.
This is a feature of the situation. We want these semi-stable points to be open, actually. Yeah.
So are you saying that the super singular curve, super singular point on the modulus scheme of elliptic curve is the most important in some sense, and so it becomes open?
Something like this. Yeah, yeah. I mean, local Langlands, we usually care about inner forms of groups. We sort of collect the inner forms together. This is Bogan's philosophy. Here, the semi-stable points will do that for us. So that's how that enters the geometry. Okay, so next I want to talk a little bit about what the strata look like, and then I want to talk about GL2, an example, and I'll draw an elaborate picture, and then we'll maybe get some sheaves into the mix. Okay, so each B, and so now I can interchangeably write a topological space of Bung G or just B of G, so I'll kind of identify them without further notation distinguishing them. So each of these we get a substack. Delta note Bung G B inside Bung G. And so again, these ambient category of stacks is a little bit frightening, but if you're careful, you can make sense of the idea that this is locally closed inside here. And what is its sort of functor of points? So S points. Exactly the G torsors instead of this. G torsors E over my Fargues-Scholze curve. S, with the property that for any map from sort of a test algebraically closed field towards my test object S, if I pull my bundle back along this map, now I have something on a curve over C, and I want to ask that it be abstractly isomorphic, but not via a given isomorphism to the bundle attached to this isocrystal structure. Okay, and this is for all such an F. Okay, so the way you should think of this is that it's we're asking that the family of G torsors be sort of isotrivial, okay, but for some very fine topology potentially. But every geometric point, it just looks like the one given to you by this recipe. Okay, so these are the families with constant singleton image inside here when you take the associated map on topological spaces. Okay. Is this definition okay? So these substacks turn out to stratify the whole space, and they're extremely explicit. So each 1GP so the form point modulo of something is something I will tell you presently. Okay, so each stratum is literally just a jerk. Where GB tilde is like a group sheaf. Which says S the automorphisms of E, B, S in the category of G torsors over the relative curve S. Okay? So this looks really bad, because maybe this group is completely inexplicit, but from the point of view of the sheaf theory that we want to do in local Langlands, there's a piece of this which is extremely comprehensible, and the rest turns out not to matter, okay, in a controlled way. So note, so the recipe that produced from B, this bundle EB, is completely functorial. And if you think about this for a minute, you'll realize that the automorphism group of this isocrystal with G structure, which Fargues-Scholze call this the E points of GB. E, in older papers, people sometimes write JB at E for this, but I follow them and write GB. This is just its definition.
But what's
Yeah.
your notation? Will it be GB or JB?
It won't be this.
And what is E now?
Yeah, that's just my weak psychology. I meant QP. Sorry. Thank you. This sits inside automorphisms. Okay, and in fact, that's even true with any S if you're a little more careful. And what this amounts to, sort of a general version of what we saw in the talk this morning. So any bundle will have a Harder-Narasimhan filtration, and the automorphisms of the bundles of the sort of graded bundle that respect a splitting of the grading will just be this, and then there will be some quotient group, which will be the automorphisms that somehow are the identity on the graded pieces, sort of the unipotent part. So from this, you can make sense of the idea that this weird group sheaf is literally a semi-direct product. And this underline I'll say something about in a second. It's a semi-direct product of this with the connection component of the identity. Okay. And this is unipotent in some sense. So for experts, this is some iterated extension of positive Banach-Holmes spaces. And in particular, when we do L-adic sheaves in a moment, it'll be just like usual sort of L-adic cohomology. If I have a classifying stack for some unipotent group scheme, there's not very many interesting L-adic sheaves on there. So that will actually play no role. One more thing on this. Because it's sort of semi-direct, you think of this stratum inside button G as both living over the classifying stack for this locally profied group and living under it. And this composite map is the identity. This one I would call S.
Clarify that G sub B is a group scheme.
G sub B is this is confusing. G sub B is a group scheme on QP algebras. G sub B of QP is a topological group, right? G sub B of QP with an underline under all of it. So this is the functor sending S to continuous functions from the topological space of S towards GP. It's natural profiling topology. So this is a group sheaf on the same test category that Bung is defined on, and it remembers the topology of the QP points of the group. Okay.
So in usual life,
Yeah.
a finite group can be also considered as a group scheme, logically. And
Yes.
here you have not a finite group but a locally compact group.
That's right.
But it still is a group options in some suitable.
Yeah, absolutely. Absolutely.
I don't see. So as we are, is there a so Bung B G maps to the classifying stack of
Yeah.
GP of QP, and
Yeah.
who maps into Bung? Is it the same? It's the same.
Yeah, and if you like, this map is a torsor for the unipotent part,
Yes.
and then this map is kind of a germ for the classifying stack of the unipotent
But a
part.
trivial.
Yeah, exactly. It's trivial. Yeah. That's right.
Should one of them be a G theta?
Here? No, I meant to write this twice. Yeah, so let me decorate it a
So
little
it's a
bit.
section in other words. So
That's
we
right.
have a projection from Bung BG to the classifying stack of GP of QP, and it's
Exactly.
a canonical section.
That's
This is
exactly
what
right.
you're saying.
That's exactly right. That's exactly right. And the moral I want to really drill home is that when we do sheaf theory, this unipotent part will be irrelevant.
And S, and you denote it by S, B, because S stands for section.
That's correct. Very good. Okay. So let's devote the whole work. I want to draw a picture. This is the picture you should keep in mind. This is it's one of those sort of only example you'll ever need sort of examples. So let's draw a picture of Bung GL2. Some colors prepared here. So let's start with sort of the most obvious point, which is the one we've already dwelled on a little bit. I can take the point where B is 1, so it's the trivial GL2 bundle. So in the notation from the talk this morning, it would just be O squared, copies of the trivial bundle. What does the stabilizer of this look like? Well, B is 1. Its sigma centralizer is just our group G that we started with. Somehow that's completely in parallel with what we saw this morning, right? Sections of the structure sheaf on the Fargues-Scholze curve are QP. So automorphisms of the trivial rank 2 bundle won't be the algebraic group GL2, they'll be the QP points of that group, right? And when you take into account the variable test object, you get that this open stratum is exactly of the form point modulo this group sheaf. So I'm going to, these blue dotted arrows indicate that I'm labeling a point in this stack by the bundle that it sort of comes from. This is an open point, and it has one immediate specialization, and the bundle that one is labeled by, again, this nice notation from this morning, is the sum of two line bundles of distinct slopes. This is the sum of O of 1 and O of minus 1. Okay? So let me write this in front to the left.
Are you doing GL2 or SL2?
GL2. There will be more in a second.
But now you're describing a single component.
Yes.
So there are components are labeled by integers.
Oh yes, we'll come to
and
that.
now you are describing the zero.
Yes, but I won't stop with this component. Okay, what does the first specialization of this look like? I have this bundle O of 1 plus O of minus 1. Again, the part of the automorphisms that sort of respect the HN filtration just looks now like GB of QP. B has two distinct slopes, each with multiplicity 1. The only option for G sub B is the maximal torus that I gave myself at the very beginning. So here I get this. And this acts, so elements here are just pairs AB, non-zero QP rationals. This funny connected thing is the Banach-Holmes space attached to the bundle O of 2. So this is some funny affine thing. And an A pair A comma B here acts through multiplication by AB inverse. Okay, it's extremely concrete.
And in this case, is it Banach-Holmes or simply Banach? I'm not.
Banach-Holmes, yeah.
Even in this case, it's not quite Banach.
There's one case where it's nice, where it's even nicer. That'll be on the other component I get to in a second. let me do one more here, although the flavor is similar. So if I look at the next specialization, I'll get O of 2 plus O of minus 2. Got my blue. And here, I'll have T of QP. But now the difference of slopes here is 4. Parentheses, yes. Okay, and that keeps going. And that turns out to be one connected component. Okay, that's the degree 0 component, if you prefer to identify the target of kappa with Z via the degree map in this case. And let me write that here. So this is degree 0. Okay, this is rather large. Let's go here. So there's a degree 1 component. And the first point in this component is already a little more interesting. So the first point is the semi-stable bundle attached to the isocrystal of slope 1/2. And so there, the bundle would be O of minus 1/2. And because there's no distinct slopes, there's no room to move some different steps in the HN filtration around. And so there's no unipotent part. And this is again going to give you an open point that looks like point modulo D cross, where D is the quaternion division algebra over dp. Okay. So this has immediate specialization, and it has to be a pair of line bundles whose degrees sum to -1. And it has to be sort of the most degenerate way of doing that is sort of closest to this. So if you think about this, you realize it has to be O plus O of -1. This already came up in Sasha's talk. This was what he called case 2 and case 1. And when he alluded to case 2 being sort of open and dense, it was exactly an allusion to the fact that the closure of this here contains this point. Okay. So I think you get the picture. The next one in that component will look like O squared, sorry, O of 1 plus O of minus 2. And here I'll have a 3. And if you keep going, you'll get 1, 3, 5, 7, etc. Okay.
So sorry, just a question.
Yeah.
So these unipotent parts that you get,
yeah,
they will generally not be abelian, is that right?
They'll generally not be abelian, that's right. They'll be sort of solvable.
Okay.
Yeah, but already for GL3, they won't be abelian. Yeah. That's right. Yeah. Yeah, it'll be some kind of unipotent iterated extension of positive PCs. Yeah. Okay. Again, I can leave myself press this a little bit. Now I actually do have enough room because you might think that I need to keep going. So here I drew some degree 0 component. Right, here's some degree 1 component. What does the degree 2 component look like? Now, it turns out you don't actually have to draw anything else to know exactly what it looks like. It will be isomorphic to the degree 0 component. Because you can tensor with the bundle O minus 1. Okay. So the open point there will be labeled by O of minus 1, 2 copies, but the automorphism group will be the same. Okay? And then the next point will be O of minus 1 plus O of minus 3. But again, you're just shifting all the numbers compatibly, so actually none of the geometry is any different. It's literally isomorphic to the degree 0 component. Okay? So you have this sort of periodicity at period 2 in the picture, and so once you draw these two components, you've seen everything. Okay? And so again, I just want to emphasize this illustrates everything I said about this general picture. Right? Each component contains a unique open point, which specializes to everything else in that component. At that open point, the stack that you're getting as this HN stratum really just looks like point modulo a locally profinite group. And in this case, at least, you see every inner form of GL2, right? Because there's only 2 inner forms. So you see the split form, of course, and then this quaternion algebra form. Okay? Any questions about this picture? one more comment. You should also think that this stack Bung is equidimensional with dimension 0. These open strata have dimension 0, and these other strata have negative dimensions that become increasingly negative. So you should think that this stratum here is point modulo a two-dimensional thing, so it has dimension -2, and this stratum has dimension -4, etc.
So, am I right that the numbers are the same as for the stack of Chibantis on P1?
It's very similar to that.
Except that in this case you don't have all of 1/2. But
that's right. That's right. This component, this looks a lot like part of.
Yes,
sort of
the numerology
P1.
is familiar.
That's right. That's right.
Of course, the reality is much more complicated.
That's right.
The numbers are.
You can think of Bung of the Fargues-Scholze curve as kind of like Bung of P1, but on LSD or something.
On what?
Some kind of psychedelic. Yeah.
So crazy, just crazy.
Yeah, that's right. That's right. But it's not like Bung of a genus 8 curve or something. It's still very combinatorial in nature. Exactly. Okay. Actually, it turns out the Fargues-Scholze curve has genus 1 minus epsilon. Making sense of that also probably would require other drugs. Okay, now let's talk a little bit about sheaf theory. Okay, now that the sort of geometry in the picture is set. And so this part, I really don't want to get into the details because this is kind of the most technically difficult thing in Fargues-Scholze. And there's a new approach to it which will be available soon, which is much more elegant.
But what kind of sheaves are those?
Sort of QL constructible Ital sheaves.
So we are QL or
Yeah.
maybe in the more refined version ZL, but
Yeah.
not coherent sheaves.
Not coherent, yeah. Yeah, we want to do something like Ital
Now
sheaf
you're
theory.
saying that, if I understand correctly, that it's something subtle. It's described in the paper by Fargues-Scholze.
That's right.
Yes. But there will be an update to it.
That's right. So Peter has some.
Which will make things simpler or more refined? Or
It'll make the technical foundation simpler, actually.
So the cohomology paper of Scholze is outdated.
No, the torsion coefficients, the story is the same, right? But with QL coefficients, they have to work very hard to build a sheaf category on which the Heck operators can act without sort of getting too large a category, right? It's this D-lease thing that they define by hand. But now Peter has some new motivic formalism. He announced that there will be a seminar on it this semester in Bonn, so I guess it's happening.
But maybe it's because they insist everything to be smooth.
I don't know. You're going in the exact wrong direction because I just wanted to say that I don't want to go into the details of this. But the moral is that you can work with it as if it were just QL sheets on a scheme or something. And I'll sort of give you a cheat sheet. Yeah.
I just have a question from Zoom.
Yeah.
The question is, what happens with GL3, and if there's ever a positive dimensional component?
No, all components are equidimensional at dimension 0. With a single zero-dimensional open point, all other strata are strictly negative dimensional. What changes for other groups is that the specialization relations are no longer totally ordered. But that's to be expected. Okay, so let's fix some L not equal to P. So for my coefficient ring, I will take QL bar. You can take other more general rings, but this is where the representation theory is simplest. So let's just say this Fargues-Scholze. Spell it right. Define categories. Let's see D, 1G. QL bar coefficients. And you can also define this category for these individual strata. So here I have some B. Okay. And there's a sensible way, as you would expect, to sort of take a sheaf and pull it back along the inclusion of the strata. I'll just take this earlier. So IB is what I wrote, right? This inclusion of 1GB, 1G. Okay, so last week we saw I1 in some of the lectures, and that was just a special instance of this. This arrow really goes the wrong way. Right, take a sheaf on the whole space and pull it back in some sensible way. And then it's a a theorem. This theorem, not a definition. That sheaves on one of these strata are actually just a derived category of the abelian category of smooth representations of this group. Okay, and if you like the functor here, you have this section over there. You should think that this is SB upper sum. Okay, so this is a category we already care about, right? If we care about local Langlands, this is just the derived category of smooth representations of the sort of groups that we really want to understand, right? It turns out that the sheaf theory on this stratum is exactly this, and this gives precise meaning to the claim I was making that the torsor part for this unipotent group here plays no role. Okay. This is even symmetric monoidal. This is sort of as nice equivalence as you could ever ask for. Okay, and from now on, I will identify this category on the stratum with this. Okay, so I'm never going to write this again. I'm only ever going to write this. Okay, and I'm also going to write IB, excuse me, upper star for this composite functor. Okay, so don't think about this. Just think about it as this, because that is what it is. Okay. Now it turns out that this IB upper star, this has a right adjoint. Not surprisingly, some kind of star push forward. You can take a sheaf from Bung and extend it in a usual manner. And it also has a left adjoint. Which denote IB sharp. Okay. This is a strange feature of the situation. This is something very special about Bung, that these functors exist and have good properties. Usually stalks along a closed, sort of at a closed point in topology or something. That functor doesn't typically have a left adjoint with good properties.
In a familiar world, the left adjoint would have been denoted by IB Sheaf.
So that functor will appear, but that's its own thing.
Just a moment. So what is?
So if we're at an open point, then sort of left adjoint of upper star on an open immersion is lower sheaf.
Yes. So should we be surprised here? The fact that it has a left adjoint.
I think you should be a little surprised at points that aren't open. Yeah.
A little bit surprised when the point is not open.
That's right. That's right. I mean, you have to make sense of the idea that somehow Bung can be like strictly henselized along each stratum or something. This is not totally formal that this thing exists. I mean, what I'm about to say is even less formal.
What is the meaning of this symbol in this strange functor? Is it natural, sharp, or
sharp? Right. So this is some way of taking smooth representations of this p-adic group. And now we have two sheaves on Bung. And it turns out this has extremely nice properties. So first of all, this functor is fully faithful. Okay, so it embeds this category really in here as a full subcategory. Okay. So that I can sort of abusively write. We have this collection of subcategories. These form an infinite semi-orthogonal decomposition. Actually, computing them in any sense is a bit hard, but this kind of soft qualitative statement is already proved in Fargues-Scholze. And again, the moral now is that you should think of this category of sheaves as really being assembled in some not too complicated way from these categories that we know we already care about with local Langlands. Okay?
Can I ask a question?
Yeah.
If it's some semi-orthogonal decomposition and that's given by some gluing atom that we need component.
Yeah.
Is this gluing atom something like explicit representation here?
It's actually really complicated. Yeah, so that amounts to the question, can you compute the composition of sort of one of these followed by upper star at another point, right? And these turn out to be incredibly complicated, these compositions. So somehow if the answer to this were easy, then like categorical local Langlands would somehow be easy. But yeah, the actual way these subcategories interact is very rich. Yeah, this is part of why this is interesting.
So you have this you had this sequence of points which all correspond to equivalent categories, like for the torus.
Yeah, that's right.
And that's still true that even if you take 2 points with it,
yeah,
and a weird endomorphism of the category.
That's right.
Okay.
And you can really compute examples. So I think on Friday we're having some kind of Q&A or office hours style talk. I want to actually show you some bizarre examples for GL2, and you can see phenomena like this. Yeah.
By the way,
yeah.
So the great conjecture says that all this is equivalent to some category of spectral nature.
That's right.
Which also has a semi-orthogonal composition.
That's a very good question.
Is it easier to understand the gluing data on the spectral side?
It's harder. Actually. It's harder. Yeah. This is actually an important component in the new work that I want to talk about. Yeah. Some spectral version of the semi-orthogonal decomposition. Well, okay, maybe
maybe one can say that on the spectral side there is some sort of semi-orthogonal decomposition one can see, but maybe they don't match exactly.
Well, I do have one that I believe matches actually in this situation.
I guess what I mean is like the most obvious one I would say on each side matches by some like uniform interchange of basic metrics.
Yeah, you can make some guesses on the other side for something that might match this, and the most naive guesses turn out not to be right, but I think we have one on the nose now with L not equal to B. So it's 253. Okay. All right, so let's carry on. So I want to change gears now to sort of set things up on the automorphic side in terms of what the picture of the basic objects looks like. Now I want to switch to the spectral side, where the technicalities are easier, and then I want to formulate this conjecture, and then by the end I want to state vaguely what we're aiming to do, and then next time I want to go into more details about the proof strategy and new ideas. Okay. So on the spectral side, we want to make sense. So the main player is the stack, which I denote R G, so it's sort of notationally on the same footing as Bung G. So this is the stack L-adically continuous L parameters. Remember, I'm assuming for simplicity my group is split, so I don't have to worry about the L group. It's more basically that an L parameter will just be some kind of homomorphism from the V group to the full group. Group G, valued in QL. Okay. And it's a little bit subtle to make this into a moduli problem in the correct way, if you want this to have good finiteness properties. But a slightly more down-to-earth way to think about this is in terms of Abelian representations. This is the functor. Setting A, say any bar algebra. So in pairs where I have phi and WQP. Into the 8 points of G hat, a group homomorphism of open kernel. And I have N, the element in the algebra, tensor with A, such that the usual twisted commutation relation holds. So phi on continuous. So I can say the adjoint action phi on continuous on N. n. And then quotient by G hat A. Simultaneous G hat A conjugation. Okay. So this gives me a well-defined functor at least from test objects towards groupoids. Then it's a theorem. There's sort of many papers where this is studied in various levels of generality, but as far as I know, all of them rely on the basic technique invented by David Helm, but I should cite Helm. Hold on.
Excuse me, what's the Q in representation?
That's just me forgetting that I specialized a little bit from my usual setup.
Okay.
Apologies. The theorem is that, and of course they prove more general results, for instance with informal coefficients, in which case this becomes much harder, or assuming G is quasi-split, which is just a slight extra technicality. But for my purposes today, what I want is the following. So this is a reduced finite type algebraic stack. It is equidimensional dimension 0 in the sense of algebraic stacks. So I can have components that look, for instance, like GM times BGM, where of course there's non-trivial geometry happening, but the dimension is 1 plus minus 1, so 0. With LCI singularities. And with a presentation as a disjoint union over some countably infinite set, some quotient stacks where you have the spectrum of a finite type QL algebra modulo some action G hat. Okay, so it's extremely nice. Okay, in some ways this whole picture is analogous to many geometric Langlands, but here there's one thing that's even better. There's no derived structure. Okay, so this stack, even if you define it a priori as a functor on derived rings, it turns out that its derived structure is trivial. Okay? Because it's LCI, essentially. Yeah, the only annoyance is that it has infinitely many connected components. But if you squint at the whole picture for a minute, you realize this is kind of to be expected. It's related to the fact that the Bernstein center in representation theory of p-adic groups has infinitely many non-trivial primitive idempotents. Somehow a spectral version of that. Okay? Right, so points here.
So in other words, it's related to the fact that the ramification can become more and more wild.
Yeah, that's right, that's right. If I, for instance, fixed an open subgroup of wild inertia and required everything to factor through the quotient by that open subgroup, I would get a finite type object. That's right. But on the other side, that's a slightly unnatural operation, so I don't do it. So at the level of QL bar points, the initial definition that I wrote is correct on the nose. And that's kind of how you should think about this. And from that language, the map to its coarse moduli becomes extremely nice. So because I told you it has this presentation as a union of quotient stacks, this automatically tells you that it has some coarse moduli map, which will be as nice as possible. So this is a good moduli space in Halper's sense. And this is now a disjoint union of affine schemes. I'll call this map Q. And both the target and the map itself on QL bar points have extremely simple interpretations. So, this coarse moduli at level of QL bar points. So exists in canonical bijection with semi-simple L parameters. So for purposes of this talk, we say it's semi-simple if it has, let's say, totally reducible with open kernel. Okay, so in Vogan's writings on local Langlands, he would call these infinitesimal characters, but I don't know, I find that term a little bit misleading. And then this map from the from the whole stack down to the course moduli. So this said some point phi to its unique semi-simplification. Okay, so in the language of Adeline parameters, what does this correspond to? It corresponds to throwing away n. You just set n to be 0. And then phi, we're not actually enforcing that phi be Frobenius semi-simple, like in usual writings on local Langlands, but now you do enforce it. You replace phi and Frobenius with its semi-simple part. Okay? That's what this map is doing, okay? So the fibers of this map sort of correspond to L parameters where the Frobenius maybe is non-semi-simple, but its semi-simplification is fixed to what you started with down here. And also variation of n is allowed, but when you go down here, you throw away n. Okay? So the geometry of the fibers of this map is actually a bit complicated. So for instance, I was confused for a while about whether there could be fibers with infinitely many QL bar points. And Teruhisa Koshikawa showed me an example on GL21. This happens. Okay, just a little bit more, and then we'll connect the two sides. So let me observe one more thing about this stack. We have a canonical map from this, for some reason I always write this vertically, down to the classifying stack that BG had, right? Well, I told you two different ways to think about the stack. In one of these definitions, it was canonically a G-hat quotient, right? So it has a canonical torsor over it. You can incarnate that torsor as this map. And this means in particular that we get a rich supply of, let's say, cohomological vector bundles. On par G. By pulling back our favorite algebraic representation of G hat. Of course, I can also think of it as a vector bundle on this classifying stack. Okay. So these, in particular, because this is built from affines quotient by this group action, so these actually generate the whole quasi-coherent derived category of this stack. Okay. And by some slight abuse of notation, I will write V both for the representation and for the pullback to a vector bundle on this stack. So now, with this preparation, I can state this theorem, which connects the two sides in a very a priori non-obvious way. So this theorem is that there exists, let's say, a canonical tensor action of this category of quasi-coherent sheaves on the stack of L parameters for G on this category of QL varietal sheaves on one sheaf. Okay, and well, how is this? What makes this canonical? Well, it's normalized by some fairly explicit requirement. And I'm being a little bit backwards by calling this a requirement. This formula I'm about to write is somehow baked into the construction of this action. But if you like, you can think I'm telling you this first. The requirement is that if you take one of these tautological vector bundles, this will give you some endofunctor just by acting by that. And this is supposed to agree with some more explicit endofunctors, which are constructed using geometric Satake. So this is some curly arrow. So this is an explicit Heck operator. Acting on sheaves on Bung. This is constructed using a suitable version of geometric Satake. This Fargues-Scholze paper is incredibly rich. It contains many, many things. One of the things they developed from scratch in that paper is a version of geometric Satake in this setting, where your Gauss-Monniers, instead of having loop groups and positive loop groups, you have de Rham rings and positive de Rham rings. Okay.
Just clarify that when you say a hash operator, that depends on a choice of a point.
So no, actually, it doesn't depend on a choice of a point. This is one of the weird miracles in this story. For us, usually you pick a point on your curve, right? First of all, we don't have a curve. We have the Fargues-Fontaine curve. But the Fargues-Fontaine curve is not well defined, because you always pick a test object. But what is well defined is the moduli space of degree 1 divisors on the Fargues-Fontaine curve. That's usually denoted div1. It's called the mirror curve sometimes, which is quite a nice name. And the miracle is that the mirror curve topologically is a single point. So there is no point to choose. This is also why nilpotent singular support is automatic for us on the automorphic side. Right? In Betty geometric Langlands, you have to enforce nilpotent singular support, right, to get that Heck operators preserve the fact that sort of things are least in the curve direction. Here the curve is div1, which is a single point. Being least in the curve direction is automatic.
So just to clarify what you said B, you're thinking about as an endofunctor of T of Bung.
Yeah, there is an intrinsic asymmetry to it. You can think of T of V as going from sheaves on Bung towards sheaves on Bung times div1, but then they prove a version of Grinfeld's lemma, which lets you reinterpret sheaves on that product as Vey group equivariant sheaves on Bung, and then you can just forget the equivariance. And that's kind of what I'm doing here. But secretly, there is an equivariance on both of them, right? This V lives over this stack. This stack has a universal L parameter over it. V will become a Vey equivariant vector bundle via that universal L parameter. And that matches the equivariance that you'll get on the output of a Heck operator. Yeah. Is that probably more even answer than I'm supposed to give? Okay, great. Okay, so now I'm actually ready to state the conjecture that I want to focus on for the rest of these talks. And so for this, I have to fix a tiny bit more data, just as in the talk I gave in the conference last week. So now, let me pick non-degenerate character aside from the key points of the unipotent radical of the Borel that I chose at the very beginning towards QLR star. And set W psi to be this compact induction from this group, which is some sort of pro-open subgroup of GFQP, all the way up to QP. Okay, so this is the Whittaker representation. So from this, we can get a functor now from one side to the other. Let me write this and then I make some comments on it. So, find a functor. Which I denote A psi. So you should think A stands for action. This is to go from quasi-coherent sheaves on this stack of L parameters towards sheaves on Bung G. And now I'm going to drop forever the QL bar because it's always going to be QL bar. And it makes these two sides look more symmetric anyway. And what does this functor do? It'll take a quasi-coherent sheaf here, and it will send it to the outcome of what I get by taking the spectral action and applying it to the extension by zero of the Whittaker representation. Okay. So this is a representation of G of QP. This functor, as we remarked earlier, for this point B equals 1, it's an open point, so sharp and shriek have the same meaning. So this is some extension by zero towards a sheaf on all of Bung G, right? But now this is doing something extremely mysterious if F is kind of a random quasi-coherent sheaf, right? Already it's hard to compute what a heck operator does to this. That's sort of the subject of my lecture last week. But now we're kind of writing down the universal way of letting a heck operator act on this, okay? So now I can state the conjecture. And again, I should say that Fargues-Scholze also formulated an integral version of this, which I don't have anything to say about. This is already very interesting. So the conjecture is that functor A psi is fully faithful and extends to an equivalence of categories. Sheaves on Bung G. And incoherent sheaves on the stack of parameters. L psi. Such that this diagram commutes. So on the one hand, I already wrote down a functor from here to here. This is this functor A psi. In general, this theory of indco is a little bit funny, but this stack is really, really nice, right? Up to this issue of components, it's just a bunch of affine schemes modulo reductive groups. So in this situation, it's actually compactly generated, and you should read the string symbols literally. It's ind of co. And because it's such a nice stack, qco is also ind of perf. And so there's an obvious functor from here to here, which is just the ind extension of letting perf sit inside co. And so this is the functor that is usually denoted by the hardest letter to write. It's capital C. This is fully faithful embedding. Right, and then the expectation is that there's actually an equivalence like this, such that this diagram commutes. Okay. Any questions about this statement? So let's sharpen this a little bit. Proposition. So first of all, a functor with these properties is unique if it exists. And it exists if and only if another functor I haven't defined yet, but I'm about to define it. This functor A psi is built using the spectral action. Spectral action is extremely nice. It commutes with colimits in both variables. In particular, it will commute with colimits. Therefore, by the adjoint functor theorem, it will have the right adjoint. Okay? So this C psi, by definition, this is the right adjoint. Let A psi. Which a priori just goes from all sheaves on Bung G towards quasi-coherent sheaves on the stack of L parameters, right? And it turns out that what we're aiming for is possible if and only if this functor restricts to give an equivalence from compact sheaves on Bung towards coherent sheaves.
So what is C?
So I defined it here. It's the right adjoint of A side. So in the parlance of classical or standard, I don't know what to call it, of sort of regular geometric Langlands, this is this functor of enhanced Whittaker coefficient. So I'll write a formula on the board. But let me just say again, and this is part of what makes this tricky, this functor A psi is defined in kind of a direct way. It's given by the spectral action on an explicit sheaf. This functor C psi is its right adjoint by definition. And so that makes it a little bit harder to work with. So this functor C psi, again, which goes from sheaves on Bung towards the quasi-coherent sheaves on the stacked L parameters, this is characterized. Say, first of all, that is collinear.
And is it clear that it takes value in coherent shapes?
Say again?
Is it clear even that it takes value in coherent shapes?
No, that's highly non-obvious. And in general, I don't know how to prove that. So part of what we're aiming to do is prove that for some groups, sort of step 0 in this program. I'll get to that in just a moment. Right, so this functor is collinear, and it's characterized by the following formula. So if I have a sort of random quasi-coherent sheaf, and I take this enhanced Whittaker coefficient of A and tensor by this random quasi-coherent sheaf and take global sections, this is the same as taking external arhams on the other side from this Whittaker sheaf towards what you get by letting F act spectrally on A. So in particular, if F is the structure sheaf, here you'll just get sort of the 0th Whittaker coefficient of A, like in my talk last week. And here you get the global sections of C side. Okay? So let me actually mention one more formula to connect this back to my talk last week. If I take the dual tautological vector bundle to a highest weight representation, and I tensor this C side, okay, and I take global sections, this is the same as this muth geometric Whittaker coefficient that I discussed in the conference. So this functor C psi sort of packages all of these together for all mu. Okay? And let me add one more point to this proposition. So I claim that this equivalence we're looking for between d of Bung and intco exists if and only if this C psi gives me an equivalence from here to here. If that C psi doesn't do such an equivalence, how do I get L? It's really silly. You just int complete this equivalence. Okay? Maybe I write this. Let's end this here. So in which case, L psi is its int completion. Maybe I should write the name of this C side on the board. So again, this is sometimes called enhanced.
Who is enhanced Whittaker?
C side.
C side.
So in the series of papers recently released proving demodule geometric Langlands, I think they call this functor LG temp. Yeah.
So you see psi is Q coholinear, so it's particularly preserves coherence.
Is that in particular?
Or what do you mean by Q coholinear?
Oh, sorry, you have to actually be a little bit careful. about this. There's some weirdness going on, which is related to something I'll come to in a second. There's two functors you can write down. One is the right adjoint of A side, and one is the dual of A side. And up to some really annoying small detail, they should agree. But it's not obvious that they agree.
Okay.
But pretend they agree. Okay? Yeah. Wait, actually, why would being Q colinear imply that it preserves colimits?
Because I thought this is
Because not everything in the source category is sort of generated by the action of Q code.
I mean, I thought it's not how we defined linear functor.
I just mean it's linear over the tensor action of QCO and the spectral action on sheaves on G. But I don't think that actually implies that it preserves colimits. I actually think what I wrote here is also okay.
Actually, sorry, does A side preserve compact objects?
No, we don't know how to prove that in general.
Oh,
But it does preserve colimits.
That's equivalent to the right adjoint preserving colimits, right?
Yeah, so I don't actually know in general that the right adjoint preserves colimits, but that's distinct from it being Q colinear. So I think what I wrote is fine. I don't really see the problem.
Well, upper if it's Q colinear, then it should preserve direct sums.
Why? Not everything in the source category is generated by like letting QCO act in the source category. So, like in some clear way. Anyway, for the groups where I can prove anything, this detail doesn't matter.
Yeah.
So let's not worry about it.
I just probably confused.
Yeah, no, I'm probably a little confused too. But this is one of the headaches that comes from this stack having infinitely many components, unfortunately. Is that like QCO is not int perf, it's int of like perf with quasi-compact support. So okay. What did I want to say? Right, so our goal is to prove this refined version of the conjecture for many groups. In particular. For GL. Okay, now let me just make a small philosophical aside. You might think, okay, this is not ambitious, why don't we just try to prove it for all groups? And the reason we don't try to prove it for all groups is that this conjecture seems to contain an incredible amount of arithmetic information, and to me it just feels completely out of reach to sort of attack it without some prior knowledge of the group in question. Okay, so this is kind of an aside. So why not? All groups. So the answer to this conjecture is information. So for instance, this is just one tiny fragment of what it implies, but already to show you that it has very rich consequences. Just the full faithfulness assumption here, that this functor A psi is fully faithful, tells you that endomorphisms of the structure sheaf on the L parameter side should match with endomorphisms of this Whittaker representation. Which is already a very non-obvious kind of thing to ask for. And then it was explained to me by Christian Hansen. This implies something even stronger looking, which I think people have been curious about, which is that for each point phi in this space of semi-simple L parameters, there exists a unique G of QP hero pi phi, whose Fargues-Scholze L parameter is the parameter that we started with, and which is psi generic. Okay. So people, it's an open question to prove that this Fargues-Scholze map from Ureps to L parameters is surjective. The conjecture would imply not only is it surjective, it has a canonical section. Okay. It means that it has a non-zero map from this W side. Sorry. That's what side generic means. It's a quotient of this Whittaker representation. So I think it's pretty out of reach without some new ideas to try to approach this conjecture for general groups. But for groups where we have a good understanding of classical local Langlands, things seem much more hopeful. And so the class of groups where I think we can say something, I'm going to give it a name. The name is meant to intuitively suggest, well, you'll see. Definition G. It's well understood. If there exists, and I'll say this on the board and then I'll say some words about it. If there exists a BG basic local Langlands correspondence for G and all its standard levies, satisfying, let's say, with.
What does it mean that exists? Can you read what you wrote?
If there exists BG basic local Langlands correspondence. I'll spell this out in a moment.
Here C stands for correspondence, not conjecture.
That's right. Let me put a small, I put a small c. Yeah. Yeah. So here I really mean we know that there's some set theoretic local Langlands correspondence for G and for the inner forms of G parameterized by basic isocrystals with G structure, which in general is not all inner forms, just some inner forms. There's a very precise conjecture along these lines in this nice paper by Caletha. It's called the local Langlands conjecture for non-quasi-split groups. And I need to assume some standard properties, some standard expected properties. I want to be a little bit precise about this. So in particular,
sorry, you mentioned some inner forms. So so we need local Langlands correspondence for G.
Yeah.
For standard levies. Did you also mention for the I understand. So here B of G basic is an adjective, so it's a local.
Yeah, that's right. That's right. And I'm allowed to replace G here with a levy also, so I'm asking for even more. Yeah. But the idea here, right, is that in local Langlands, in its most refined form, you have an L parameter, and then you usually have some extra information, some representation of a centralizer group, and then this is supposed to parameterize some automorphic data, right? And there are different flavors for what centralizer group you can take in this theory. And there's one approach where there's a natural map from these pairs, we have an L parameter and some extra data, towards the basic elements in B of G, okay? And this is what people sometimes call the isocrystal form of local Langlands. I think this was actually invented by Koppitz, but somehow Caletha was the first person who wrote it down. And you won't see all inner forms of the group necessarily, only the ones that come from a basic element in B of G. Okay? So this has a technical meaning. And again, let me just write a little bit, and then I'll say some soothing words about how you should feel about this. It's very simple. Okay. So what properties do I need this to have? So I want it to have finite fibers. This is one of the standard expectations. I want the expected parameterization of discrete series and supercustal L packets. And I want the endoscopic parameterization. For these particular kinds of L packets. So when I say expected parameterization, I mean that all the discrete series reps are disjointly partitioned by the L parameters, which are discrete in the usual sense, they have minimal centralizer size. And then a supercuspidal L packet by definition means that everything in it is supercuspidal, not just some of the stuff, and these should correspond bijectively to irreducible L parameters where n is additionally identically 0. No monotony. Okay, so this is quite a lot to assume because I'm assuming it not only for G but also for its levies. Okay, so which groups are well known? Oh, and I need one more thing, which is going to make this even more ridiculous. And which agrees up to semi-simplification.
sorry, what is it? The endoscopic chair.
Character identities, which I misspelled. For discrete series L packets. And I also, but finally, need to know that this agrees up to semi-simplifying with the Fargues-Scholze construction of L parameters. So this is quite a lot that I'm giving myself, but it's still of set theoretic nature, and that's the point, right? So we're starting with sort of a good understanding of set theoretic local Langlands for the group, now giving ourselves a more reasonable goal. Can we upgrade this to some categorical equivalence, right? And just so that this doesn't seem void, let me point out, so the following groups are well known, well understood, also well known. So first and foremost, GLN is well understood. So here, of course, there's a huge amount of work on classical local Langlands for GLN by Bernstein, Zolovinsky, Kritzko, Bushnell, many people, and then sort of finally Harris-Taylor, and now there's multiple approaches to it. And then also, let's say GSP4. Get to some PS2 for some technical reason, but that's being removed by some people. The odd unitary group, which comes in several flavors. So here you take, okay, actually in my setup today I'm only allowing split groups. This is quasi-split, but you can adapt everything. One that splits over an unramified extension. Also odd special orthogonal groups, which is work in progress of some other people. So this is not a vacuous situation to put ourselves in. That's the point I'm trying to make. Okay. Questions about this?
For example, special linear group is not well understood.
It probably is. Yeah, actually it is. Although, I might have to sweat a little bit to give you a precise written reference for this part, for instance.
Yeah.
You know, the literature on these things can be a little bit of a mess, but yeah.
Just out of curiosity.
It's morally well understood, yeah. Yeah, actually changing center is a little bit subtle with respect to like these properties. So Kalepa has thought a lot about this. Okay. So I can tell you, let me tell you the goal in one more, slightly more refined form, and then I'll tell you one more piece of input, and then I hopefully will end by stating some theorem. And next time I want to talk about the proof strategies here, sort of the new structures. Okay, so the goal is to prove the categorical conjecture. It's sort of the long-term goal for well understood. Groups. Okay. So here's the first result in that direction. This I hope I can give some flavor of all the main ideas next time, which is that the conjecture is true for GL2. Say work in progress. To establish the same result. And again, let me emphasize that I'm really giving myself access to everything I put on this board to sort of full power of set theoretic local Langlands. And in this case, I also know that I can incarnate local Langlands in the cohomology of things like Shimura varieties, or even their local incarnations, things like sort of the Drinfeld tower and its variants, right? So it's somehow not surprising, maybe, that this family of groups you'd be able to say something about connecting with this Fargues-Scholze thing, but upgrading it to this categorical statement is still still not obvious how to do that. Okay. So there's one piece of control that we need to give ourselves. And I want to talk about this because I don't want to claim that this is like fully done yet. This is somehow its own work in progress. So let me label this as key working hypothesis. I'll state it and then discuss its status. So we assume that this functor C psi is compatible with Eisenstein series. That diagram sheaves on Bung. Let's say I have some parabolic with a fixed splitting of its Levy quotient. I have sheaves on Bun M. And then, as in Linus's talk last week, we have this functor that we know with ISP Shriek, which brings you towards sheaves on Bun G. And this group and its standard Levy both have their own C functor. This one I would denote C psi M, this one I would denote C psi. And here I would have quasi-coherent sheaves on the stack for L parameters for the Levy. And here I have quasi-coherent sheaves on the stack for G. And this functor has spectral incarnation. Spectrum. Maybe I have to write course. Since it's in the QCO setting, it's not sort of the true int code one. And we assume that the diagram, this diagram commutes. Okay. So in
when you say commutes, is that a property or a structure?
it's a structure, and
Okay.
it's equipped with the datum of a commutation. Oh. Yeah, that's right. And so this is proof. So in demodular geometric Langlands, I think this is sort of a long time expected result. And there's a written proof in the third of these 5 papers, which was recently released. This also relies on forthcoming. Just to be clear, it's proved in usual geometric Langlands. In the third of these papers, and this relies on forthcoming work of Feynman. Hayash, okay. And a separate project, which I don't want to dwell on at length in these lectures, is to prove this key working hypothesis in our setting in all cases. Okay, and so in this setting, this is proved. For GL2 in particular, which is why I am stating that theorem unconditionally by Lucas Mann. So there's a manuscript that's currently being edited. This case is simpler than the general case because the Drinfeld compactification turns out to be smooth, the boundary strata are linearly ordered, the Whittaker datum on the unique Levy is rather silly. So there's certain things that make this case sort of more doable than the general case. So the general case is work in progress. Myself and also Lucas Mann. So I think I have a few minutes, more than a few minutes. So in whatever time I have left, I may actually end a few minutes early. I want to, in broad strokes, state the strategy, and then next time I want to dive into the different pieces of this strategy. Okay? Maybe there'll be some time for questions. Okay, so we're back to the goal at the top of that word. So the strategy for the goal, we sort of split it into 4 parts. So part 1 is to show, and I'll write this and then dwell on it a little bit, that C psi lifts the functor. Psi, sheaves on Bung G. Whereas incoherent sheaves on the stack with L parameters, which is continuous with continuous right adjoint. The right adjoint will play an important role in the whole theory. I denote this R psi, so you should think L stands for either Langlands or left adjoint. R stands for, well, right adjoint. I don't know if there's anyone's name I can also get it to stand for. Okay, and let me point out, being continuous with continuous right adjoint is a very strong property, right? In fact, this is equivalent to asking that it preserves compact objects. Okay. And what do I mean by lifts? Well, I mean that earlier we had this funny functor that I don't like writing on blackboards, which embeds QCO inside IntCo. That functor has a right adjoint, which is usually denoted capital C. It sort of projects IntCo back towards QCo, right? If you think of this as the incompletion of Co, here you're just literally incompleting the standard inclusion of Co inside QCo. Okay, so this functor loses a little bit of information, but all the information it loses is at minus infinity. And in particular, on the sort of obvious copy of Co here and the obvious copy of Co here, it's an equivalence, right? Now C psi is given to us a priori, and it goes diagonally like this. And so asking for this to happen, asking to be able to lift this to a functor here, which is continuous with continuous right adjoint, that can be done if and only if you have proved that this has the finiteness property I wrote on the board over there. So this is equivalent to showing exactly what Professor Balanson asked earlier. C psi will carry compact sheaves on Bung G, where it's coherent sheaves with spectral parameters. Okay. So let me say this one more time. I'm asking for something weaker than the whole conjecture here, right? I'm just asking for a functor that here makes this diagram commute that has these good properties. That functor exists if and only if this is true. In which case, that functor is just the incompletion then of C psi restricted to here. Okay? So step one is to actually show this finiteness property for C psi. Okay, and again, I don't know how to do that in general, but for this class of groups, there is a way to do it that I want to discuss next time. Please.
Would you recall the strategy tomorrow?
Sure.
Because otherwise, I'm not sure that with references I'm unable to. And I'm already tired, so.
Could I take one more minute? I think I can actually finish everything in 1 minute. Yes. There's 3 more sentences. And then, yeah, then I'll be perfectly set up for tomorrow. So thank you for indulging me. Okay, 3 more parts. Part 2, we showed that this right adjoint preserves compact objects. Part 3, show that this right adjoint is fully faithful. And part 4, show that this L, this left adjoint, is conservative. And that's the strategy. So if you have an adjoint pair of functors and one is fully faithful and the other is conservative, then they're mutually inverse equivalences. And so, sorry for going over, so to speak, and I'll explain this in much more detail tomorrow. Okay.
Sorry, can I ask some questions?
Yeah.
So one is, sorry, I don't know if you see this, but so is it correct that G of Bung G is compactly generated by
Yes.
the explicit compact object?
Yes.
From presentation theory? Okay. So, but it's, as you were saying, it's not so easy to compute
psi is really hard to compute. That's right. Like full faithfulness of a psi is equivalent to computing this. So this is true if and only if a psi is fully faithful. Right, because it's an adjoint pair of Q colinear functors, so you just have to know what happens to the composition on the unit in Q code. And it is the composition on the unit on the left. Right. So that's sort of the basic issue with all of this. C psi is hard to work with. And so you have to give yourself leverage. Other questions? Maybe I can just say out loud so that no one on Zoom thinks I'm saying something overly strong. Parts 1 and 2 are currently okay for all well understood groups. Part 3 we can do for GLN for sure. Part 4 we finished for GL2. And we have a strategy for GLN which is purely on the spectral side now. So I'm very confident we'll be able to finish it, but I don't want to say I've checked all details yet.
Can I ask a question from Zoom?
Yeah.
So the question was, where do you use the endoscopic identities? I was surprised that went into well understood.
Yeah, that's a really good question, and I hope I can explain that a little bit tomorrow. It has to do with the difference between a representation being supercustal and a representation having supercustal L parameter. So there's some strange representations, like for GSP4, there are these non-generic discrete series representations, which have a, there are these non-generic supercustal representations which sit in the same L packet as a generic discrete series. And it's hard, for instance, to prove anything about C psi on these weird supercustals. And if you use the endoscopic character identities, you can kind of massage them into a good situation. So this actually uses this paper I wrote with Jared Weinstein and Tasha Palefa a few years ago. So it does actually enter in a key point, and I'll try to explain it tomorrow a little bit more.
Any other questions? So we meet tomorrow at 10.
10, yes.
And then we meet on Friday also at 10.
Okay, 10 is the
10.
settled time for Friday. Sounds good.
Yes.
Great.
Meet tomorrow.
Yeah, coming back.
You did? I did get it.
Yeah, you can seem to
She wants to.
Since now, what do you
yeah, please.
Okay, find these.
Yeah.
Maybe I
So you define the definition of
That's right.
No. You don't need to. I have a